Alright, so we continue with MOSFET circuits at DC. This time we'll study one of the most important circuits of this semester and do some detailed analysis of DC analysis of this circuit. Same numbers, so this time we'll have a PMOS, so mu1 Cox W by L is 4, mu P Cox W by L is also 4. The threshold voltages are equal in magnitude, of course opposite in sign. Alright, so these are the two things we need, Vt and mu Cox W by L. Here is the circuit. So last time we had an NMOS here, now we put a PMOS here. Alright, this is called a CMOS, common source amplifier. This is the workhorse of a large number of CMOS amplifier circuits, as we shall see throughout this semester. So the numbers are in fact the same, the transistor is different. So Vg1 is 0.9, Vg2 is in fact 2 to start with, and the question is find the drain current and the drain voltage. Alright, please pause and solve this circuit. This is, as I said, this is an important circuit to learn to solve. Alright, so as usual we say, well, let's assume both the transistors are in saturation. Write both the saturation region currents. Alright, I'm keeping on emphasizing, write both the currents. So ID1 in saturation, we've seen this many times, 2.9, 0.4, so you get 0.5 milliamps. ID2 for the PMOS, and this is the first time we are encountering a PMOS. So this is mu P Cox W by L by 2 is still 2, VSG minus mod of VTP squared. Alright, VS 3, VG is 2 minus mod of VTP is 0.4. That turns out to be 0.72 milliamps. Alright, now the currents are not equal. The currents of course have to be equal, Kirchhoff's current law at this node. Therefore, what does it mean? That means our assumption that both the transistors are in saturation was not correct. So one of them must be in triode. Which one? One of them has to be in triode. Which one? Alright, let us think about this. If we have a transistor in saturation, the current through it is constant. If the current is in, the transistor is in triode with the same gate source voltage, then the current in it will be smaller. Alright, this IDVG plot is for the same gate source voltage. Now here we have two transistors whose gate source voltages are fixed. Okay, let me do this. So the gate source voltage of the NMOS is 0.9 volts. The gate source voltage of the PMOS is 1 volt. Mu P Cox W by L are equal. So both transistors have the fixed gate source voltages. One has a higher saturation current than the other. Now this transistor, let's for the sake of example, look at M1. Can M1 carry 0? Right now it's carrying 0.5. Can M1 carry 0.72 milliamps in this circuit? Even though with these numbers? The answer is no, because M1 can carry a maximum of 0.5 given that the gate source voltage is fixed. Can M2 carry 0.5 milliamps? M2 is currently in saturation. It carries 0.72. Can it carry 0.5? And the answer is yes, because a transistor can always carry a current lesser than its saturation current. Given a gate source voltage, it can carry a lesser current by going into triode. Alright, so in this circuit, the answer to this question is the transistor which has a larger saturation current has to go into triode in such a circuit. Alright, whenever you have two transistors in saturation, in series, and the saturation currents are not equal, the transistor that has a larger saturation current must go into triode. Alright, so that is what will happen. Okay, so I put this in blue because it's a very important thing to remember. Alright, so in this circuit, M2 will go into triode. Once we figure that, then we of course just write the two drain current equations, equate them, and the only unknown will be VD, and we solve. So we'll get a quadratic and we find VD. VD is 4.77 or minus 2.97 volts. VD can't be 4.77 because VG2 is 2 and 4.77, well, what would 4.77 do? That is higher than 3. The current will have to flow up, right, in the PMOS, which is not possible. VD can't be negative because this is negative. The current in the NMOS will have to flow up, which is also not possible. So here is the thing. If we find that both the answers are not correct, alright, obviously both these answers are not correct, that means that we, or I should say I, have made a mistake. One of the answers has to be correct. Alright, so I want to talk about making mistakes. We all make mistakes, silly mistakes, when we are solving problems and solving equations. And it is okay, it is human. What is important is that when we finish solving a circuit, we pause, we stare at the answer and we ask ourselves, is this answer reasonable? Alright? Because often the tendency is, and especially this happens when you are in a rush, where you want to quickly solve, find some answer, go to the next problem, and so on and so on. But then you are not doing it right. Okay? You must pause. You say, well, does this make sense? Is this the answer coming out as it should be? And if it is not, then you go back and check, well, I have made some mistake. I must find the mistake and correct it. Alright, this is an extremely important skill. It must become a habit to check numbers and ask if the numbers are reasonable. Alright, now in order that you develop this skill, this is a little thing that I am going to do. So what happens is when you find the answer, sometimes the silly mistake will cause the answer to be reasonable, sometimes it will cause it to be unreasonable. Now if this happens, so that if your answer is in an exam, that your answer is not correct, if the answer is not reasonable, I will cut a lot of marks. If it is reasonable, it is wrong but reasonable, I will cut very few marks. To emphasize that if it is unreasonable, you should have caught it and you should have gone back and checked whether the answer was reasonable or not. Alright? Okay, that is one. Now let us say you made a mistake and you got an answer that's not reasonable. Then the next thing, of course, you do is to find that mistake. That is another skill that is absolutely essential to acquire. I'm sure you know this already, but I'm re-emphasizing. To debug equations, it is like debugging a computer program. We all make mistakes while writing programs, but then the compiler catches these mistakes most of the time and it tells us, here there is no compiler. So we have to learn to find the mistakes. Alright, so that of course you have to acquire the skill. Alright, so let's go back to that problem. So the M1 was in saturation, T was in triode. We wrote this equation. Then I wrote this equation, and this plus 4.8 was incorrectly calculated. The correct number is minus 1.8, and if we put minus 1.8 and solve, we'll get the two values for the drain voltage, 2.73 or 2.07, and then we have to make sure that whichever value puts M1 in saturation and M2 in triode is the correct value. So in this case, in fact, both the values put M1 in saturation because they are both greater than 0.9 volts. So whichever puts M2 in triode And for M2 to be in triode, VD has to be greater than 2.5 volts, which we just saw a couple of minutes ago. So greater than, or did we? Maybe not. Let us see. In fact, we'll see it here. So M2, for M2 to be in triode, VD2 has to be greater than VG2 plus mod of VTP. And for our circuit, that this is the condition, 2.4, not 2.5. And so 2.73 is the correct answer. All right, so that's the answer. We've solved it with VG2 equal to 2 volts. Now let us increase VG2 to 2.1 volts and ask ourselves what will happen. So qualitatively, first of all, as VG2 is increased, the source gate voltage of the PMOS decreases. So the saturation current of M2 will decrease. Alright, earlier it was 0.72 milliamps. The NMOS current was 0.5 milliamps. So M2 was in triode. Now this current has decreased. So let us calculate that current. So with VG2 equal to 2.1, M1 we already know is 0.5, the saturation current. We find for M2, so ID2 with VG2 equal to 2.1 also turns out to be 0.5 milliamps. So now we find that both the currents are 0.5 milliamps. Therefore, M1 and M2 both are in, the assumption that they are both in saturation is correct. And okay, so fine. So now we must find the drain voltage, right? Then we would have solved the circuit. So what is the drain voltage in this circuit? All right. So you please pause and think about it. So I'm carefully using the word think about it. All right. Before we go to the MOSFETs, let us for a moment look at this circuit. So there are two ideal current sources connected in series. Both carry the same current and there is some voltage at the top. We are asking what is the voltage VD in this circuit. And this is a circuit question. It has absolutely nothing to do with MOSFETs. This is your first course in electric circuits question. What is the voltage VD? Can you tell what is the voltage VD? And often the kind of intuitive answer that immediately students tend to give is it must be 1.5 volts. This is 3, VD has to be half of 3 volts. So my next question is, can you prove it? Can you use some circuit law or circuit theorem? So usually when we solve circuits, we always apply some circuit theorem, right? Or law, KCL, KVL, something we apply to find voltages and currents. Now which law or theorem will give us VD equal to 1.5 volts? And the answer is there is no law that will give us 1.5 volts. In fact, the answer to this question is that VD cannot be found in this circuit. VD can be 0, it can be 3. For all we know, it is 5, it can be 25 also. There is nothing to prevent it from being anything at all. Alright, there is nothing. No circuit law is violated by VD being any value whatsoever. So our answer is we don't know. All right. The answer to the question what is VD is we don't know. Okay. The MOSFET, this circuit, the CMOS circuit is the same as this circuit if we neglect channel length modulation. So if we neglect channel length modulation, then M2 and M1 behave as ideal current sources when they are in saturation, which they are in our circuit. We just found that with VG2 equal to 2.1 volts, they both are in saturation. Therefore, this circuit is identical to this circuit, and therefore we say VD cannot be determined. The answer to the question what is VD is we don't know. All right, we don't know VD in this circuit. Okay. Realistically, of course, the MOSFET is not an ideal current source in saturation because of channel length modulation. And so there is effectively one can say that the MOSFET is an ideal current source in parallel with some source resistance. And as soon as we have the source resistances, Vd can be found. Still, in analog circuits, because the source resistance of a MOSFET is very high in saturation, and its value in reality is very difficult to exactly determine, we say that nodes such as these are high impedance nodes, and we will continue to make the statement that we really don't know Vd even if channel length modulation is included. All right, so and why is this? Okay, the reason for calling it high impedance we'll see later, but I want to make a observation that in our previous circuit, in the previous lecture, this was an NMOS. So the source was connected to this node of the NMOS, in which case Vd was very well determined because VGS is very well determined. It is the drain voltage that is difficult to determine when the transistor is in saturation. The source voltage is always well determined. All right, and here two drains are connected together of two transistors in saturation. That is why this is a circuit where Vd is very difficult to accurately predict. What we can do at the same time is we can determine the range of Vd, because we have determined that M1 M2 are in saturation. So we can say, well, to keep M1 and M2 in saturation, Vd has to have a certain range, right? Vd has to be greater than 0.5 volts to keep M1 in saturation. Vd has to be less than 1. I'm sorry, this is not looking correct. Sorry, this is plus. We just saw this is plus for a PMOS, so this is 2.5 volts. Okay, so this is, so the range of voltages for which, the range of drain voltages for which both transistors stay in saturation is 0.5 volts to 2.5 volts. And therefore we say that as long as M1 and M2 are in saturation, the voltage Vd can be anywhere between 0.5 and 2.5, and we don't know anything about it beyond this, knowing this range. All right, I want to make another comment because we talked about MOSFETs as current sources. So we'll talk in more detail about this later, but I just want to make an observation that a PMOS, when the gate and source voltages are fixed, that transistor can act as a current source if it is placed in saturation. All right, so as long as the MOSFET is in saturation, it behaves as a reasonably good current source, and so does the NMOS. Both of them, when they are placed in saturation, they act as reasonably good current sources. And a PMOS current source looks like this. So the top terminal is connected to VDD, and one can connect anything on the bottom terminal. The NMOS, the bottom terminal is connected to the lowest voltage in the circuit. It could be ground or minus VSS, and one could connect any circuit to the top terminal, and that circuit will sink current that is determined by the NMOS transistor. So we'll come back, and in fact there is a whole chapter on current sources and current mirrors. All right. One more thing. Suppose I am given this circuit and nothing is connected to the drain. So I take a MOSFET, I ground its source, I connect a 0.9 volt to the gate, and I ask the question, what is the current flowing in this circuit and what is the voltage at the drain with nothing connected? It is open circuited. What do you think? What would be the current? What would be the voltage? It's an open circuit, so no current flows. No current. KCL will be violated if current was flowing. All right, so that's the first thing we say. No current is flowing in this circuit. If no current is flowing, what is the voltage at the drain? So one way of looking at it is to look at this IDVD characteristic. So we say some gate voltage. So let us I don't know which one. None of this is correct actually, but anyway, let us say this one is the IDVG characteristic for the given gate voltage of 0.9 volts. So the operating point must lie on this characteristic, and we also know that the current is zero. So if the current is zero, we are at here at this point, and if the current is zero, the drain voltage must also be zero. This is the ID-VD characteristic, right? So we say the drain voltage is zero from this characteristic. But we can also think about it and say, well, because there is a gate voltage, a channel is formed. So MOSFET is providing a conducting path between the drain and the source. So conducting path exists with no current because the current is zero. So if a current is zero in a conducting path, the voltage across that conducting path also must be zero, and therefore the drain voltage of this MOSFET is zero. Alright, so both are zero, the current as well as the voltage. All right. Okay, now let us add one more transistor to our circuit. This is a basic cascode. We'll talk about cascodes more as we go along. So what we've done is we had M1, an NMOS and a PMOS. Now we've added another NMOS in between the PMOS and the NMOS. And let's think about, let's analyze this circuit. Now, so before we analyze quantitatively, we make an observation or couple of them. One is that the gate and source voltage of M1 are fixed. The source is 0, gate is 0.9. The gate and source voltage of M3 are fixed, 3 volts and 2.1 volts. The gate voltage of M2 is fixed, but the source voltage of M2 is, it will vary depending on, it will adjust itself based on the rest of the circuit conditions. But the fact that M1 and M3 have fixed gate source voltages implies that they have fixed saturation currents. Alright, because the saturation current is determined by the gate source voltage. So M1 will have a certain saturation current, M3 will have a different or the same saturation current. If these saturation currents are different, as we saw in the previous circuit, whichever is the smaller saturation current will be the current in the circuit, and the larger saturation current transistor will go into triode. Alright, so in this circuit, of course, we already saw that with 0.9 and 2.1 volts, M1 and M2 both have the same current and it is equal to 0.5 milliamps. So that will be the current that will flow in this circuit. Alright, and as this source of M2 will adjust itself so that M2 also carries the same current, 0.5 milliamps. Alright, okay, so I have written all this here. So M1, M3 is 0.5. Now, because again, okay, from the circuit before this one, which was in the last lecture, M1 and M2 are identical transistors. They are carrying the same current. Therefore, their gate source voltages are also equal. And therefore, in fact, we had solved this circuit with M1, M2 last time. So the source voltage is 2 minus 0.9, which is 1.1 volt. Alright. And how much is VO? The drain voltage. The drain voltage cannot be determined because there are M3 and M2. Both the drains of M3 and M2 are connected here. And therefore, we say, well, we can only find the range of VO. We cannot find the actual value of VO in this circuit. Alright. Now suppose we decrease VG2, this one. So VG2 where we had made it 2 volts. Okay, so in fact, I think it will be good for you to revise the last lecture because we did a lot of the discussions there already. So VG2 is made less than 1.4 volts. M1 will go into triode. We had seen that last time. All right. So if VG2 is made less than 1.4 volts, this voltage will go below 0.5 and therefore M1 will go into triode. Now if M1 goes into triode, its current has to be smaller than its saturation current. And now if the current in M1 becomes less, then the current in M3 also must become less because the same current is flowing. Now if current in M3 is less than the saturation current, then M3 will also go into triode. Alright, so for Vg2 less than 1.4, M1 will go into triode, M3 will go into triode, M2 will stay in saturation. Because why is that? Because if M3 goes into triode, VO is going to go close to 3 volts because a triode implies that the source drain voltage of the transistor is small. So VO will be closer to 3 volts, well, it will be above 2.5. How much will it be? Well, whatever it will be. Yeah, if this is 2.1, then VO will be above 2.5 and VG is less than 1.4. So this is VO is much greater than VG. So M2 will stay in saturation. But we still don't know the saturation current because we don't know the source voltage. So we'll have to solve this circuit. So, okay, so I am not solving this circuit. I am leaving it to you to solve this circuit. It is not difficult. It is just writing 3 equations. So we'll have to have 3 equations and 3 unknowns. ID, VS2, VO are the 3 unknowns. 3 drain currents you have to write. Okay, so next lecture we'll start small signal analysis.